I'd like to welcome you all to this presentation. My name is Sina Shaham and I'm presenting this work on behalf of the other authors, Professor Gabriel Ghanita, Ritesh Ahuja, Professor John Crum, and Professor Cyrus Shahabi. This work is focused on proposing a new method for private publication of location histograms. I start by going through the introduction and some of the basic concepts. Then we'll have the problem formulation followed by the reviewing some of the related work. Then we'll have the proposed framework, and finally we'll go through the experimental results both on the synthetic datasets as well as the real-world datasets. The basic setup of system model is as follows. We have the database D of user locations on the map, and based on that one, we generate a histogram of the map, meaning that the counts of user on each one of the areas on the map. Then the database curator, which is considered to be trusted in our system model, wants to release this histogram to the public. On the other side, we have the data analysts who make these count queries to understand the population of different areas on the map. And of course, the goal is to answer all these queries such that the privacy of users is not compromised. So the means to achieve privacy here would be based on the metric called differential privacy, which is the commonly used metric for a statistical database, data and databases. The principal idea here is that the existence or absence of an individual should not impact the output of a query by a large margin. This large margin is defined based on the closely related concept referred to as sensitivity. The sensitivity value for count queries for the histograms is set to 1. Also, differential privacy here is compromised based on this the constant epsilon, which is referred to as the amount of the budget that we have for achieving privacy. There are two commonly used methods to achieve differential privacy. The first one is the Laplace mechanism, in which a draw of Laplace noise is added to each one of the counts on the histogram. I have an example of this scenario for a simple setup on the right-hand side of the slide. You could see this histogram in which each one of these numbers represent the population of an area of the map, and we have sanitized them based on the Laplace mechanism, and the sanitized values are shown on the bottom right of this slide. The second mechanism that we have is the exponential mechanism, which uses a distribution to actually achieve the differential privacy for the histograms. The problem formulation is as follows. The problem that we are trying to address is as follows. We would like to generate a differentially private histogram of the database D such that the expected value of relative error is minimized. Meaning that if we have this workload with different shapes and styles, we want to have the relative error with respect to the non-private histogram minimized. Prior works an approach for achieving private histograms can be categorized in 3 groups. The first one is a data-independent algorithms such as flat-tree, which do not really depend on the distribution of the users and counts on the map. They have shown a better performance for larger maps. The second group is the partially data-dependent algorithms such as UG and AG. These algorithms are based on the total count of the data points on the map and do not consider the distribution itself. They come up with this new granularity for the grid and then apply the Laplace mechanism to sanitize the data. Despite the simplicity of the algorithms, they have been shown to have a really good performance in terms of the relative error. Finally, we have the data-dependent algorithms, which do consider the distribution of the users on the map. Although so far the approach in this category have had the poor relative error performance compared to the other algorithms. So our proposed algorithm framework is referred to as homogeneous tree framework, which is a tree-based algorithm and aims to partition based on the data density and homogeneity. Some of the key features that it has is that it could actually apply its private stop conditions to prevent over-partitioning in low-density areas and under-partitioning in high-density areas. And based on the experiments that we have, we show that indeed it can provide a higher utility with the other benchmarks in the literature. HDF includes two interrelating mechanisms. The first part is the differentially private partitioning. And the second one is the sanitization part, which is referred to here as data perturbation. As I said, the partitioning part of the approach should also be differentially private to preserve the privacy of users on the map. The total amount of the budget that we have, the privacy budget that we have, is split into three parts. The first part is the partitioning budget used for identifying the grouping different cells on the map. The second part is used for the data sanitization. And finally, we have this small amount of budget used for height estimation of the tree. Our proposed approach is based on this hypothesis that a determinant factor in actually achieving a high utility for the data set is the homogeneity of data. So we would like to ideally keep the cells which have more or less similar group to cells which have more or less similar values together. And the question, of course, becomes how we could actually detect the homogeneity on the map. For this purpose, we actually propose a new objective function and use KD3-based algorithm to achieve this objective. At every split of the KD3 algorithm, the HDF algorithm would evaluate the objective function for a set of candidate sets. And here we have this differentially private algorithm on top of these candidate sets and chooses the one which minimizes the objective function. Ideally, among the candidates that we have, the one which provides the highest homogeneity is selected for further partition. We prove in the paper that the sensitivity of the approach that we have is upper bounded by 2. Okay. Here I go through the general setup of the framework that we have, HDF. So starting with the original histogram represented here by A1, we use a small amount of budget to sanitize the total count and get the estimation of the height of the tree. Then once we have the estimation, we are able to optimize the amount of budget allocated to different levels of the tree. This is done for both the sanitization and partitioning part. Then we recursively generate the child nodes. Upon arrival to a new node, what we do is we sanitize the count of that node. Once we have the sanitized counts, we actually evaluate them based on different stop conditions. And this is being done privately because that count is sanitized. And these stop conditions could be based on the number of users, the density, or any other objective user-defined objective functions. And in this process, as we go forward for generating new nodes, we keep track of the amount of budget. So if the stop conditions are checked and tested and they are satisfied, then the tree is pruned and the remaining amount of the budget is used for updating the sanitized count of the node. Otherwise, we continue the process for doing further partitioning on the grid. Finally, once all the leaf nodes are generated, we'll publish the sanitized leaf nodes to the public, which represent the sanitized counts. So we compare our approach with different benchmarks, both data-dependent algorithms, data-independent algorithms, as well as the partially data-dependent algorithms. I would like to actually go through our last graph that we have, in which we actually have all the algorithms together, evaluated on both synthetic data sets as well as a data set taken from Los Angeles. So here on the x-axis, you could see the different algorithms, and on the y-axis, we have the mean relative error performance in log scale. So you could see that on average, the diamonds represent the average for each one of these algorithms. And you can see that on average, HDF could perform better than the other benchmarks in the literature. And the point here is that when the underlying data is more uniform, other algorithms can catch up. Algorithms such as, let's say, AG and UG would be able to catch up with the HDF, but for more skewed data sets, because they are not designed for uniform, the UG and AG are only designed for uniform data, they perform much worse than the algorithms such as HDF.